This is okay. So before we start, this is a presentation about and a workshop about basic introduction to Kubernetes and cloud native computing. And before we begin, I just wanted to give you a bit of my background. I'm currently working in Ubisoft as online programmer. I have about 7 years of experience. Most of it is in cloud native development. I'm a certified Kubernetes application developer. I've worked with many startups in the same space, and many of the products in the same space. Uh, Nearly all of them have Kubernetes as their deployment strategy. So and about in the presentation, if you like, after every few slides, I'll stop for questions. So if you have any questions, we can address them then and there. Right. So I will share this presentation after the fact. So is a list of resources that you can utilize to set up your development environment, let's say, or if you want to go through some of the interactive tutorials or some of the resources that you want to try things on. Uh, I, I will share this presentation so you can have access to these resources. I have a simple script that sets up my development environment. Feel free to use that if you want. Um, all right. So let's quickly start with differentiating cloud and cloud native. So cloud has been around since AWS really. So AWS kind of made cloud ubiquitous, and everyone started deploying their applications on cloud. And it has been around for quite some time. But what it means is that you move your entire infrastructure to basically somebody else's computer, right? So you don't care about where it is, you don't care about how it's managed. You just pay for your use and you move your entire infrastructure there. That does come with quite a bit of redundancy, primarily being the system that you move is largely redundant, and you pay for that redundancy. So cloud basically refers to your development and deployment on cloud-based infrastructure, something that you do not control or do not manage, but is managed for you as a service. It could be as a platform, but is managed for you. The entire infrastructure is managed for you as well. Uh, Cloud native, however, refers to application development in containers, microservices, and dynamic runtime orchestration. Now, this could run on any cloud. It could very well run on your own machine. It could run on your own data center, right? So the reason it's referred to as cloud native rather than cloud, it's primarily because the way of looking at application development is fundamentally different. We look at application as a set of containerized microservices that, again and again, microservices have been around, and service oriented architecture have been around for quite some time, but it only makes sense in the context of Kubernetes, well, not Kubernetes, in container orchestration, wherein you can create the smallest possible subset of your services and deploy that independently, iterate on it independently, and then go ahead and deploy it anywhere you want, right? So that is basically what refers to cloud native development. So cloud native can be thought of as a subset, although not proper subset of cloud. So you can deploy your infrastructure on cloud, and then that infrastructure will host your cloud native applications, right? Um, all right. So I spoke in the previous slide. I spoke a little bit about container orchestration, but before that, let's talk about what are containers, right? Uh, Containers are, and again, containers have been around for quite some time. Containers existed in Linux as a separate process, like segregated process. So that's at the heart of containers. It's just a Linux process separated from everything else, right? So Linux has multiple layers of segregation that it allows. Once you separate the process, so on Kubernetes, there is a C group and namespace. And When you separate a process at these two levels, it basically exists independently. It has access to system calls because it is a process running on a system. So it can basically call all the kernel calls that it needs to do. It can call all the system, it can make all the system calls that it needs to do, but it pretty much exists on its own, and you don't actually require any particular software to create containers. You can basically create containers on a Linux system using a simple unshare command. It's not, it wasn't particularly fancy. What makes it so is that it then, once you separate it out at a process level, it becomes a standalone process. It's a standalone executable package. You can put anything you want in that. That basically is separate from everything else, and by virtue of being a process, it's lightweight. So in our context, container then becomes a standard unit of software that wraps up all the code and all its dependencies. Container image is basically a compilation of all this information into something that can be executed on a machine. It is effectively a file system. It holds all the files along with the things that you want to execute, and we use some sort of container runtime mechanism to run those, right? So it includes your code, includes your runtime engine. So for example, if you are running a Python code, then you would need Python engine to run it. If you're using a Node.js code, then you need a Node.js installed on it. Similarly, depending on programming languages, you would need those runtimes. You you probably also need some of the system tools that do not form the basis of default images. So if you're using something that is not part of the standard default image that you're using, you probably need to install that as well, and some of the libraries and settings. So all of these things put together form a container image, which can be run by a container runtime, right? So when we use container runtime and use it to run this container image, we get a running container, which is just a process on a system. It used to be the case that uh, the way things work in Linux and Windows used to be quite different. But for all intents and purposes, now everything has been standardized. Uh, so you need this container runtime to create a running container, right? And this container runtime, the most famous one is Docker. It's just a container runtime that allows you a functionality to create a running container. It also provides a bunch of other things, but at its core, it's a container runtime engine. Other examples include Containerd, which eventually will become standard in next year, probably. So Docker will no longer be the standard. Kubernetes will replace that. So Containerd is also a container runtime engine. Um, the differentiation between virtual machines and containers is often the same differentiation between cloud and cloud native. When we talk about AWS and having your application deployed on AWS, what we basically are saying is that you have some virtual machine created on AWS, or it could be GCP or anywhere else, or in your own, even your own data center. You have some sort of hypervisor that creates a virtual machine which acts like a server, and you put everything that you want in your application there, and you run it. And that's basically how you get an application deployed in cloud. Whereas in container, uh, you don't you would require some sort of virtual machine to run your container orchestration platform. But once you have that, uh, a lot of the overhead is handled by that container orchestration engine itself. So the differentiation between virtual machine and containers is pretty much the differentiation between cloud and cloud native, right? In virtualized machines, the entire hardware is virtualized, whereas containers only whatever components that come from uh, whatever components that come from your application are virtualized. All right. So do you have any questions so far before we move on? This kind of forms the basis of what we're going to talk about from here on.
Feel free to put them in the chat if you want. I think so far.
All right. So
someone asks, will Docker be obsolete?
I'm sorry?
Will Docker be obsolete?
No, Docker will not be obsolete. It'll just not be the Kubernetes standard. So currently, the Kubernetes standard is Docker engine. So when you basically deploy Kubernetes through standard deployments, the default engine of execution is Docker. Although I don't remember from which version of Kubernetes, nearly all container runtimes are supported. Eventually, uh, container D will next year. It's very likely next year. I might be wrong there. It could be this year, but very soon, container D is going to become the standard of deployment. Docker is not going anywhere though.
Thank you.
All right. All right. So moving on. So yes, the types of deployment, right? So we know the traditional deployment is what used to happen before there was cloud. You would have hardware, there would be an operating system on top of that, and you would have a bunch of application deployed. Extremely inefficient use of resources. Uh, Much of the resources, as we know, on server are not utilized. They just stay there for us to pay for. Extremely inefficient way of deployment. Then that got replaced by standard cloud deployments, which AWS basically popularized. AWS started consuming their own services, their own infrastructure as services, and then those services they eventually started selling. Uh, Herein, you add a layer of hypervisor to the collective infrastructure. Now, the hardware here is a collective hardware, not one server or two servers, but it's a series of servers. And they all have operating systems. Each of them has hypervisors, and then there is a there is a vertical separation and horizontal scaling of this underlying hardware. What that means is that you can have extremely large number of servers put together to form some sort of what AWS calls availability zone, and have multiple of these servers capable of creating virtual machines on the go. So, and then these virtual machines will have their own operating system. They'll have their own libraries and application binaries and application configurations and networking and that kind of thing. And then that basically runs your application, right? Much better than traditional deployment, which existed about 15, 18 years ago. Much better than that. Although not quite as efficient as where we can go with containerized deployments, but significantly much more resource utilization than previous ones. Uh, the the scope of compute virtualization, which means your CPUs and your CPU related resources, not memory, but CPU and CPU threads. The virtualization of that is quite resource conserving. So you can actually split your compute a lot before it becomes a problem. That's not necessarily the case with memory, because it just doesn't split that well. Compute splits the best. So for most of the time CPU is not being used, or even if you go and look on your machine, CPU is hardly ever consumed, whereas memory seems to be most consumed because applications sort of dump everything there. So this saved quite a bit of computation power. But with container deployment, we can actually narrow down to a process level what we are consuming and then control that. And that's what the container deployment is. So here again, this hardware is not a single server, it's a series of servers. They'll have their operating systems and each one of them will have a container runtime. And on top of that container runtime, we will be able to create containers which will be a self-containing processes that contain everything that they need to run. So it works on my machine is no longer an excuse. So if you have something working on a container, it's going to work everywhere. As long as your container runs, it's going to work everywhere. So that uh, joke is gone basically. But there are some networking cases where it still applies, but your application would still work. So these are the three types of deployments, and we are moving to the right hand side to container deployment, and we are getting much more efficient at that. So uh, we are building more and more products so that we can deploy even complicated components of infrastructure such as service mesh and network components and reverse proxies and all hard components basically to virtualize in a containerized environment so that we can control environment in a more software uh, defined and declarative manner than ever before. So that's the great news. What that means though is that there is a lot of work that is happening which requires applications to be broken down from virtualized deployments into microservice based deployments. Fundamentally, because when you moved from traditional deployment to virtualized deployment, uh, there wasn't a pressing need to break down your application. The fundamental change was in how application was deployed, right? Instead of having application deployed in your garage in a server room, you would have that deployed on AWS, but nothing fundamentally changed about how applications were being built. Even though service oriented architecture did exist, the services were clubbed together and not let uh, loose in a separate deployable pipeline. So all services were sort of put together, even though the application was sort of conceived as a set of services. All of those services were traditionally developed together and put together and deployed together. Uh, but when you have containers, you can you actually do need to break your application down to manageable pieces. Otherwise, this container just becomes as large as a VM, and there's virtually nothing to be gained by having that large of an application. So the natural shift becomes toward when you move toward a container deployment is that you break down your application into manageable pieces. And one of the really good examples that I've come across in my own personal career, a professional career, is that a lot of the times your application, almost all of the times, your application is not used in an uniform manner. For example, let's say you have 25 services in your applications, in your application. Let's say you're building a bank application. You have a bank application, and again, bank is not probably not a good example. Let's say you have some sort of mutual fund application. You purchase mutual fund, right? And you have a bunch of things that you can do there. You can transfer money to your account. You can purchase mutual funds. You can sell mutual funds. You can list all the top performing mutual funds and who manages them and all of that. And all of these are going to be different services, right? In microservices world, uh, all of these are going to be different services. But the service that's going to be consumed the most is going to be probably auth. You do need some kind of authorization or authentication or authorization, and that's going to be the service that's probably going to be consumed the most. But apart from that, not all of the services are going to be consumed equally. Most of these services uh, will have some sort of priority. There'll be some uh, mechanism by which we'll be able to determine which service gets consumed, usually through metrics, which service gets consumed the most. Not People are not going to go and buy uh, mutual funds as much as they are going to go and look at the list of mutual funds, right? So two different services are going to be used in a disproportionately different manner. But if you have a single application that has all your services put together, then that does not scale well, because when you are trying to scale, when you reach, let's say, when you are serving 50,000 customers and your infrastructure is under stress, and you say, yeah, I need to scale my application, the way you're logically going to scale that is you're going to scale the entire application, because your entire application has that particular service and it's not separated out. But when you go toward a container deployment, you can only scale the specific service that is consumed a lot. So in my uh, uh, career, I have seen that specifically auth is one of the most used services. But apart from that, no no two services are generally scaled at the same level, because the consumption just doesn't scale up to that level. That when you increase the load, there are going to be very few services which require very large number of resources, and other services are not going to have that level of consumption. So one of the great things about container based deployments, it doesn't have to be Kubernetes. It's just the idea of containerized deployments, is that you can scale independent to microservice, and that has always been the promise of microservices, is that you can iterate on microservices separately, you can develop those separately, you can deploy those separately, right? Continuous deployments just make it possible to do those in a much more reliable and scalable and maintainable manner. So that's really the way to look at it. Like, if you have a piece of your application that is going to be used very widely and very extensively, then it stands to reason that you should be able to scale that particular part of your application independently of other things. And that also is a really good use case for breaking down services to a point where uh, each service roughly resembles a one large set of functionality, but only one large set of functionality. You know, it should do one thing really well, but only one thing, right? I mean, like, that's really the way to look at that. So it's not that it's changing the way because it's popular. It's getting popular because it's changing the way applications can be deployed and can be scaled in a realistic manner. Uh, do you have any questions pertaining to this?
Yeah, actually, someone's asking, are containers just mimicking runtime environments, aka allowing you to mimic multi-threading at a large scale?
The way to look at containers is that they are processes running on your host. They're just processes running on your host. So when you know run your application or run anything, it's a process that's running on your host machine. Uh, so that is exactly what a container is. Container runtime is just a mechanism of getting you there, right? So you can pretty much create containers without having to have any of the container runtime. You can use, Linux. You can use your Linux Mojo to create, separate process. Use unshare. The tool is called unshare. You can use that to separate out process. Container runtime is just a mechanism to get you there. So the right way to look at that is a process running on your machine that is separated from everything else.
Okay, thank you. Someone else is following up. Do all container-based apps just address one service?
Uh, that is actually a complicated question. So generally, you can have more than one service in a container. So technically, you can have. There's nothing stopping you from having that. You can have any number of services in a container. Basically, you can have a container as large as a virtual machine and host deploy your entire application there. And so there's no technical limitation on doing so. But you lose all the advantages of containers when you do that. So the standard way of deploying in a containerized ecosystem such as Kubernetes is that you have one functional container, uh, that holds one functional service. Like each container sort of holds one service, like a microservice. And then if you need more of that service, so if you are getting more requests for that service, then you have more number of these containers that hold that particular service. But one container would have one sort of microservice that does one specific job. That is the standard way of deploying things. Kubernetes does not have the concept of uh, the the concept of container at its core. I mean, the smallest object in Kubernetes is actually pod, and we'll talk about that when we get there. And the pod can have more than one containers, but not of different services. So uh, it's really not a good idea to put multiple services in the same containers, because you lose the advantage that comes with the services. There is some case to be made about the size of the services. For example, you can't really have one function in a container, right? You can't go as low as that. You can't say that this container will only execute, string replacement or substring calculation. That's very counterintuitive, because you'll be consuming more resources to run containers than to actually get anything done. So that's why a microservice per container, or per set of similar containers, is the right way to look at things. Is that a microservice will be able to do one job really well. So for example, authentication could be a microservice, which means that it does authentication. Like if you have a login service, it'll do uh, it'll be in one container. If you need more login, if you're getting very large number of login requests, then you'll have more containers of the same login microservice than you have of anything else, let's say. But that service that's running inside the container will do the entire login flow. So it'll do authentication, authorization, it'll probably do some validation and whatnot. So bunch of other things. It'll test what rules you have, and generate tokens and whatnot. Any number of things that authentication service might do. So, but it'll be an authentication service inside a container, not a specific function there. We can't go that low, because that is also a very counterintuitive approach. You can't put too many services in a container. At the same time, a container should not represent a single function, because if you want to represent a single function, then there is a different mechanism for that, a serverless mechanism, which does use containers, but it does them in a slightly different mechanism. So containers are very short-lived there. Containers in general are short-lived, but on serverless models they work slightly differently. I'm not sure we'll cover serverless in that, but in today's presentation. But if like at the end of the workshop, if you have any questions that I might, and if you have time, I might be able to answer those. Does that answer the question?
Yeah, actually, just one last one. It doesn't really make sense to use containers if you don't have if your architecture isn't microservices then?
Uh, there are use cases to have, so there are use cases for containerized orchestration in absence of microservices, but it is limited. So if you have a completely monolithic application, if you have a single large application, then there's not much use in using containers directly. So the way a lot of the organizations have been going about it, and that's largely the majority of the work that is happening, is that applications are being rebuilt or being broken down to fit the new deployment mechanism, because the amount of money that you save, the cost benefit analysis of this is just ridiculously high, because you don't waste your resources on things that are not being consumed in that proportion, which would happen in a virtualized deployment. So you probably, if you have like a single monolith application, then you probably would need to break it down for containerized deployments to make sense. But most applications do have some sort of services put together, because service oriented architecture has been around for quite a while. So it's just all of those services are put together. So separating those out is not as difficult as rewriting the entire application or breaking down your monolith into microservices. But you would need some sort of work there for things to fall in place.
Okay, that makes sense. Thank you. Thank you.
All right. So moving on. Right. So I think we already talked quite a bit about containerization. So containerization is use of container deployments to deploy your infrastructure and to have your ecosystem built around that. Um, we already talked about why should we care. We care because the cost benefit analysis is very good. So you save quite a bit of money. You also manage your, and money is of course one part of it, but the even bigger part of it is that your application becomes much more manageable. For example, Netflix, I believe, releases every single day. So it's, yeah, I think it's every single day. Uh, because they have their application built in such a way that they use most of their deployments in a cloud native manner. GitHub basically runs entirely on Kubernetes. So when you have an application that has its components separately deployed, if there is a problem with one component, you don't need to redeploy the entire application. You can just redeploy the part of your application that's a problem, you know, uh, and it's not really that big of a deal. Your one of your functionality might not work for some time, but it will not bring down your entire application. Well, unless your auth service is down or login service is down, in which case it will. But uh, most other services will not bring down your application, right? Microservices. So, and that is the purpose of this. We can iterate on one specific part of your application really quickly, and if you have pipelines built around that, then every time you push something, when you have everything tested, it automatically goes wherever it needs to go and it gets deployed, and users hardly ever notice the difference. And there's another way to look at that is that if you wait for application deployment for, let's say, 6 weeks, right? If you decide that you're going to update to productions every 6 weeks, what that means is that if there is a problem, that if your code has caused some sort of regression, then you don't know about it until 6 weeks. It misses your testing or test pipeline because you don't have 100% test coverage, and it goes to productions, and then you have to figure out where it came from. Whereas when you're redeploying every day, you know where it came from, because there are going to be very small number of commits that go every day. There's only so much development you can do in a day. uh, when I first started, we used to deploy 4 times, well, 2 times a year. We used to have two major releases. Then we went to four, a quarterly release, which meant that you could have bug in first day of your quarter and not figure out what went wrong until you release it 3 months later, and then it's just a you know version control, history checking to find out what happened. Not a great use of time. Then within 6 months, we actually were able to reach a level where we broke down our application to a point where we could deploy fairly frequently, and by that I mean every alternate week. In my current team, we deploy fairly regularly, once at least, but sometimes more than once a week. So that's really the way to look at the application, and that kind of control is affordable to us because of the small size of containers, right? Uh, and yes, so because you have very small pieces going in, if you optimize your workflow, you'll really have very small builds, uh, generally few minutes worth of builds rather than hours of compilation. Small enough services get compiled really quickly because they are only targeting specific part of it. And microservices and service-oriented architecture and the role of small deployable units. I think we already covered that. I see a lot of questions, so let me go there. Um, Yeah, so it's not really great when you are releasing by that fashion. When you have a service, you really want to deploy it as quickly, as frequently as possible. The purpose of software is to provide a service. It's not to stay in deployment phase. And the role of software engineers or software developers should really be to develop new features, new things, and new products, right? That's We are engineers. We should be engineering things and not spending most of our times, which is what I used to do in first 6 months of my career, in deploying applications. We literally would need roughly 18 hours for the entire build to complete and to deploy. It wasn't really an efficient use of time. So uh, that is something that allows us. The containerization is something that allows us to do all these things. Um, all right. Yes, Docker Engine is a container runtime. It was open sourced in 2013. It provides a registry of container images, but now you have lots of other container registries as well. For example, GCR, which is a Google Container Registry, is a very, very popular one. And Docker provides a declarative representation of container images, which we can which which we can use to represent what a container image will have, so that when we build it, it remains consistent. Docker also has its a file system, which is a layered file system, which maintains each of those statements that we write in Docker files in a layer, so that if whatever changes between the layers can be tracked, and uh, to basically provide quicker implementation of uh, building, and and more importantly, your image can be used by somebody else, and that image can be used by somebody else, and that image can be used by somebody else. So it's a sort of layers. So if you have an application that does something, and I really want that application, but I want that application along with some, let's say, caching. Your application does not implement caching, then I can have my uh, caching implemented and just use your image, and insert some local caching code. A really crude example, but I think it works. Um that way I can reuse everything that you have done. At the same time, I get the advantage of adding on top of whatever you have done, and that is possible because of the Docker's layered file system. So I have an example that I can share with you. This is the Docker file, and this is due to this PowerPoint thingy, but ignore these early pointers, the pointers at the beginning of the lines. Those are not there. But really, the way to look at Docker file is it's a sequence of steps, and each steps decides something that's going to happen, right? So uh, the first is saying, I'm going to write an application. It is going to be a shell script, and that shell script is going to do something, right? But in order to run shell script, I need a shell runtime, right? So as we saw in earlier slides, that if you're running, let's say, a Python code, you need a Python runtime. If you're running a Node.js code, you need a Node.js runtime, right? So same thing for shell, you need some sort of shell runtime. It could be bash, it could be zsh, it could be sh, any number of things. So in my case, I want bash, let's say. So I'm pulling from bash :latest. Now this latest is a tag that basically tracks the version of the image in Docker. It uses semver notification, semver mechanism, which is basically major version, uh, major version dot minor version dot bug fix, right? So you can see .0.0.1. So, and then you can have hyphen any number of things. So it's called semver. It uses that tags. Latest is a way of saying whatever is the latest image. It's generally not a good idea to use latest tags in your applications. When you're deploying applications, you probably need, so Docker used to have latest and stable, but now the standard way of using is using specific version of your image. So let's say I want bash 31.0 or whatever, right? So I don't even know if 31.0 is a bash image. It's available, but just as an example, right? So a specific version of your image, so that if anything changes in the bash image, you're not impacted by it. In this case, if somebody, if upstream latest image is broken, then my code will not work. The reason I put latest is to just emphasis on the fact that you should not be using latest when you're doing production deployments. If you want to test things, latest is fine. And latest, almost like most of the times there'll be no problem, but there are cases when this has broken flows in the early days of Docker, when people didn't know that latest is not a great way to do things. So ideally you should be saying bash colon version of the bash image. Then work directory is a directive that says where are you going to, where are you when you are inside the execution tree, where exactly are you, right? So and that also uh, uh, and this is for the execution of Docker build, not for Docker run, right? When it's not for Docker, it's not when you're running the container, it's when you are building a container image. So work directory tells Docker the the location on which you are going to put your resources when you are putting your resources. So that's the work directory. It also does that for the execution runtime, but the first step is to put resources that you want to execute. So in this third step, you can see copy script.sh. So script.sh needs to be locally present, of course, and then that will be able to move. So copy from location on your machine to a location on inside the container, right? So if I wanted to rename that file, I could have renamed it at this type from script.sh to something else.sh, right? Uh, so that's the copy directive. CMD is the execution directive, so that's the one that is run. There is also entry point, which basically tells what's the entry point, and that can be overridden at runtime. For our purposes, CMD works fine. Uh, we are saying use bash to run this script, and that script is probably going to print something, right? Docker build, this command basically builds your Docker image. It's going to tag this image called bash hello world with 0.0.1. That is the first tag that we have, that we will tag it with. The tag could be anything as long as it follows similar syntax. And then Docker run will actually run that container. Uh, yes, any questions here so far?
What's the tag for?
The tag is to show the versions of that image, Docker image. So you can have any number of images. For example, your script.sh changes. Your first script.sh said hello world, and next thing is going to do something else. Then it's a different container image. So the change in the container image shows that something has changed. So that's why we track that using tags.
Okay, makes sense. Thank you.
All right. So container orchestration. So about containers is that containers are standalone and ephemeral. Containers by standalone, it means that they execute by themselves. They are isolated processes running on the host. And by ephemeral, they're short-lived. So they can die. A lot of things can happen to containers because a lot of things can happen to your host, and then host will respond to those things like termination events or not enough space or any number of things, and containers can die. And we shouldn't really care if they die, right? Because they're processes, and any number of processes die when you're working. We see many times things don't respond as quickly. We kill those processes, we start those again. It's fine. The problem is network security, liveliness, and storage are some of the concepts, but not all of them, but some of the things that we do need to take care of. We do care about what happens to our files. If we have something running on our server, if it dies and if it comes back, as long as there is no impact on the service, it's fine. But if it's writing something, if it is, let's say, writing the names of users that it logged in, then we do care about that list of usernames, presumably, because otherwise why write them? So we do care about those. So we do need to protect that information. We do need to ensure that if a container dies and comes back, there is no impact on service. There is no impact on our service, that calls made by users from the outside world are reaching us. That is something that we need to ensure. So that's where network comes in. Also, if a container dies and comes back, we want to make sure that the security is not compromised just because a container died and came back, or a new container was scheduled, or more number of containers were scheduled, or less number of containers were scheduled from previous state. There's no impact on how secure our application is. We also need to ensure that if a container dies, our service is not impacted. So just because a auth container is dead does not mean auth service is dead. Two different things, right? So we need to make sure of that. But if we use our Linux Mojo and create a container on Linux system using, let's say, a tool Unshare, we would need to manage those things ourselves, because Linux is not going to do that. For Linux, it's just a service, right? So if it dies, it'll tell you that it has died. That's the best it's going to do. It'll dump bunch of logs about what happened, but that's pretty much it. It's not going to make sure that it comes back. It's not going to make sure that things, network calls reach us. It's not going to make sure that the new container that you create is going to be just as secure as the previous one if you don't follow the exact same steps, and that kind of thing. So we need a platform that takes care of these things, right? And Docker is a container runtime. It also provides a mechanism to do some of these things, definitely, but not all of these things. For example, Docker does provide a network mechanism. It does ensure that pods get the correct IP address. Uh, it provides some sort of networking layer. So it does do that. But apart from that, it doesn't provide much. Now, Docker did have other things that do not come with standard Docker distribution. One of those is Docker Compose, which is a container orchestration platform. In Docker Compose, we basically provide a declarative mechanism of what our container infrastructure would look like, and Docker ensures that it remains that way. It was one of the early container orchestration things that came up. Uh, One of the problems that exists with container uh, orchestration engines such as Docker Compose is that it doesn't have constructs other than the ones that exist in Docker. So it cannot do things. For example, it cannot detect, load, and increase number of containers. Uh, you really can't do that in Docker Compose. And there are many such things that form the uh, critical rule that form the critical rule of management, application management in containerized application deployment. So Kubernetes is just another container orchestration engine. It came out from Google when it was Borg. Google internally used an engine called Borg, which they open sourced it a few years ago, and then it became Kubernetes. Now it's a completely open source community managed software. It's a container orchestration engine that provides many logical constructs on top of container runtime that allows us to look at Kubernetes as application delivery mechanism rather than container orchestration. So when you're talking about container orchestration, you should really be focused on, can you or can't you deploy application as a logical construct on that container orchestration system, because when you think of virtualized deployment, when we in the earlier images we talked about traditional deployment and virtual deployment, and the only major thing that changed was that it was being deployed somewhere else, right? And there was a more efficient use of compute. uh, However, there was a mechanism, a logical construct of mechanism, is that your application will run inside a system just like it does on your system, and the networking will be managed separately, the security will be managed separately on the outside, load balancing will be managed separately. But when you come to containers, you can't really manage those things separately, because containers are ephemeral. So if you manage those separately from your application deployment, then you also need to manage the life cycle of whatever things you create outside of these things. So if you have a service network mesh that is managed outside of this, then you can't really imagine your application to exist as one. uh, you really should be able to imagine your application, or being able to architect your application as a set of logical constructs on a container orchestration system. So Kubernetes is one of those systems. Docker Compose provides exactly the same mechanism for that, although it's not as sophisticated as Kubernetes. Any questions so far?
Is there any reason you would use Docker Compose over Kubernetes?
Today, no.
Okay.
Uh, so actually, there are a few cases now that I think about it. So if you have a very minuscule deployment in a local context, then you don't want overhead of managing a Kubernetes cluster. There is a use case for that. But generally speaking, with smaller and smaller, there's, for example, K3s, which is a very small Kubernetes deployment. It's a bare minimum Kubernetes deployment. So not really not really a good use case anymore. But there are a few use cases on very small, infrastructure, where you don't really want to where you don't really want scale, or those things are not really your concern. There might be some use case for Docker Compose, but at a production level, there's hardly anyone new that is choosing Docker Compose over Kubernetes. I know a couple of IoT-based companies that do use Docker Compose quite extensively, because that is something that they have been using for quite a bit of time. They moved to containerized ecosystem long before Kubernetes was a stable and viable alternative. So they've been using it for quite a while, and one of them is actually moving toward Kubernetes. So uh, I'm not sure if IoT is anymore like a good use case for Docker Compose anymore.
Okay. You mentioned overhead for Kubernetes, but not for Docker Compose. Would Docker Compose not have that?
Can you say that again?
You mentioned having overheads with Kubernetes. Would Docker Compose not have that, or not as much at least?
So yes, that was one of the early problems with early Kubernetes versions, is that there were too many services that needed to be deployed. But there are variants of Kubernetes that provide a very stripped down version of Kubernetes that deploys bare minimum services. So there is a significantly less overhead with those. And as with Kubernetes, new services are getting added every few weeks. So those solutions might be better suited than uh, than than Kubernetes for those use cases. For example, if you have a setup of Raspberry Pi, K3s might be better suited than K8s. It's called K3s. It's a very stripped down version of Kubernetes. Not sure what's the development stage of that. I was quite interested in that at one point, but it's a very bare minimum version of Kubernetes. Um, right. So moving on. Yes. Kubernetes is a portable, extensible, open source platform for container orchestration. What it means is that you basically, there is a certain set of components that you have to deploy, and then you can enable other features if you want. It's very extensible, and we'll talk about what that means. Is you can basically write your own controllers, your own operators, your own resource types in Kubernetes. It's very extensible, and Kubernetes API will not discriminate against those. It will treat those in the same way it treats its own resources. So it's very extensible. Uh, it's uh, it's open source. We already talked about that. It was open sourced by Google in 2014. It has a declarative structure of objects. Uh, what that means is that you declare what your object would look like, generally in YAML. You can also do that in JSON, but YAML is the standard declarative structure of an object. And Kubernetes will ensure that what you represent in your YAML is reflected on your cluster. So that's basically what Kubernetes is. If you say I want an Nginx controller running on my machine, you say I want a container that is going to be named Omkar Nginx. It's going to have image Nginx of version, let's say 12.3, and it's going to be there are going to be two of those running on my cluster. So Kubernetes will go to a public repository, uh, pull the Docker image, create the required number of containers with the name that you have provided, and if you have provided some configuration environment variables, and inject those containers with the information that you have provided, and ensure that two of those are always available. So if you move from, let's say, 12.3 to 12.7, it's going to delete the previous two and create two new containers with 12.7 image. So that's the purpose of Kubernetes. That's what I mean by declarative structure of object. You write them in a YAML that is representative of the state that you expect it to have on the cluster, and whatever you write there, assuming that it's possible, Kubernetes will ensure that it exists. And it provides native objects with controllers. So Kubernetes is extensible, quite extensible. You can have your own objects, you can write your own objects, and Kubernetes API server will treat them pretty much the same way it treats its own objects. However, it only provides controllers for its own native objects, obviously. You can write controllers for your own objects, and Kubernetes will again treat those controllers this pretty much the same way. There is a slight bit of difference, but for the most part, pretty much the same way it treats its own controllers. So, right. This is the architecture, and this image comes from Kubernetes. This is documentation. I just wanted to go through the components and architecture of all Kubernetes uh, standard Kubernetes deployment. Right. So Kubernetes is a container orchestration system. It can be deployed anywhere. I have one running on my VM on my machine. You can have it. You can have it running in Google Cloud, Amazon Cloud, OpenStack, anywhere on your private cloud, wherever you want, right? Because it's just a set of applications that need to be deployed together. So now Kubernetes has two things where work happens. So you have a control plane and you have data plane. So control plane is where your core components reside. These components, like the fundamental component is like all of these are sort of core components. But the most important component is the persistent store etcd. It's a key value store. It's a memory store that stores everything in a that it's sent to that is sent to it. The default configuration is etcd. You use it to store everything that you create. If you create any number of containers, and Kubernetes has a concept of pod, which is a wrapping on top of containers. Any number of controllers, load balancers, services, configurations, uh, tokens, secrets, uh, network configurations, any of that, all of that information is stored in etcd. That is the persistent store. So this is the component that stores all this information. In a standard Kubernetes deployment has three uh, nodes in a control plane. That is just to help with leader elections. You can have any number of nodes, preferably odd number of nodes, so that leader elections go fine. Uh, and etcd basically is deployed there. So you'll have those many number of etcd instances running. They'll store all this information. The core component that looks after the container creation is a kubelet component running on the worker nodes. So the worker nodes, the kubelet runs on all nodes. It basically is responsible for creating all your workload, all the workloads, all the containers and everything. Um, there is API server, which is the point of contact. So every time we talk to Kubernetes, we are actually talking to an API server, and that's really the central piece of communication. There are multiple instances of it, obviously, depending on how many nodes are there. Again, in a standard deployment, there'll be 3 nodes. That's the one that we talk to. We have a scheduler, which is another core component that runs on the control plane. What scheduler does is it determines where to put your container. And there are several mechanisms by which you can influence that or directly control that decision. Although controlling that decision for every container is an awful lot of work. So that's not really how you'd go about it. But you would generally influence if you really need some containers, some set of containers to be deployed on some set of nodes, then you would use a mechanism to influence the decision of the scheduler, but you would not enforce it. Uh, because unless there's an absolute need, for example, if you have a component, if you're building a game, let's say, and you need GPU on a machine, and you only have 5 nodes with GPU and you have rest of 75 nodes without GPU, and your application only works on a machine that has GPU, then obviously you need to put it, redirect it to any of those 5 nodes. But you would not pick a specific node from those 5 nodes. You'd say, I want it on a node with GPU, but that's what I want, and you figure it out. Uh, so yes, there are cases for that, but on a broad level, you would try to not pick a specific node for your deployment, because if something happens to that node, you're left in the wilderness trying to figure out what happened. So and then there is an impact on your availability of your service. So if you really need to choose to prefer how to do that, and we'll talk about how to do that. There are several ways to do that. Um, there is a kube proxy. Now, kube proxy is something that runs on every node, and it is a proxy. It basically proxies requests here and there, everywhere. Basically, it's one of the core components. There is a controller manager. Again, it's not an optional component. It's the controller manager. This one is a core resource that looks after the life cycle of controllers, and we'll look at what kind of controllers we have. Even if you write your own controller, the controller manages the piece of thing that's going to look after its life cycle, mostly. And there is a cloud controller manager, which is sort of optional. It basically is for cloud provider API, talk to cloud provider to perform operations. But rest of the components are the core components that form the Kubernetes master. Kubelet and kube proxy basically run on every node there, uh, to determine what happens to your workload. Any questions so far on these components?
Oh, good.
All right. Perfect. So Kubernetes features. So some of the things that it provides on top of Docker, we'll just go through this. It provides service discovery, meaning that you can have many number of services deployed on any number of containers. Uh, Again, one service can be in containers, but one container should really have uh, no more than one service, microservice. So it provides a service discovery mechanism in which if your container dies and comes back with a different IP, Kubernetes will ensure that the traffic is redirected to the correct container. It provides a load balancing mechanism. So there is, if you have large number of requests, those requests are load balanced properly. It provides storage orchestration. You can create a persistence storage, meaning that storage that will persist unlike containers. So if container dies and comes back again, it can attach itself to the previous containers storage and then take it from there, so that there's no impact on the service. It basically goes to things as usual. It provides rollbacks and rollouts. It provides some of you must be aware of the blue green deployment. So it basically allows you to roll out your new features in a manner is that does not impact your service. That basically does not impact not only your service availability but also the ability of your service to serve that load. So that's one of the features. It provides a state machinery for objects. It maintains, as we saw in the previous slide, it maintains all the objects in its CD store. So it provides that state machinery. It provides configuration and secret management. So it provides two resources through which you can store your configuration or your secrets, which can have potentially uh, confidential information like your tokens and that kind of thing, or AWS tokens and that kind of thing. It is self-healing, meaning if your container dies, it does its best to bring it back to the state that you said is required. So if you said you need 23 instances of something and two of those containers die, Kubernetes will do everything it can to create two new more containers so that the desired state always matches the current state. Uh, it is extremely extensible. You can create your own objects, your own controllers, and they are plugged into Kubernetes as if they are Kubernetes's own native objects. It provides stateless and stateful applications. By stateless, you have applications that do not require a particular state. Most of your application, for example, login service that we talked about, is going to be a stateless application. In most cases, there are some cases where it could be stateful, but in most cases, it's going to be a stateless application. It's a REST-based service. You send your credentials over over wire in a secure manner using TLS SSL. And once your call reaches the login service, it gets those credentials and checks whether you have access to do whether you are who you are. First of all, that's authorization, and then whether you have access to do what you want to do. That's authorization. It's going to do both of those things, and then it's going to send you a token, let's say, that you can use to perform further calls, and that's done for the login service, right? And then if it dies and a new container comes up, it doesn't really care uh, whether things work. Your token is going to be stored in your database, so the database is completely separate from the service. There is no state involved in the login application for the most part. So that's a stateless deployment. But you can also have the stateful application. For example, if you wanted to deploy a MongoDB in Kubernetes, then that would be a stateful application because, well, It is a database and it does require state. There are many other examples of stateful applications, but stateless applications are the most common way of deploying uh, your applications, your microservices. So I have a few of those things that is to help you get started with Kubernetes. Like when you want to get started with Kubernetes, Kubernetes in Docker is a great way to run Kubernetes on your own local machine. Kelsey Hightower is one of the engineers in Google. He has written Kubernetes the hard way, wherein you can create all the resources yourself to really figure out how things work, create secrets, secret management, and set up TLS, all of those things. Uh, and you can follow. Again, I'll share the presentation after the workshop, so you can have access to these resources. Okay, so to access the cluster, we use kubectl. We have Kube kubectl is a kube controller tool written to provide you access to the cluster, right? So what it does is it connects you to the cluster and then it forwards your request to the API server. Now it uses kubeconfig, which holds the configuration of your cluster. It uses that as a mechanism to first to detect where is it that your request needs to be redirected. So that's the IP address of your port, IP address of your cluster. Second, what certificates does kubectl need to use to point to wrap to securely wrap your requests, uh, so that would be server certificate. Three, if you have more than one of these configurations which specifically want to use, and fourth, do you really have access to the resource you are trying to do? All this information is contained in kubeconfig. Context comes into place. Context is how kubeconfig separates multiple clusters. So if you have, let's say, 4 Kubernetes clusters, and you don't need 4 different kube configs, although you can have those, but you don't really need those. Context is how those are separated. Your context will have all the kube config, uh, all the kube configurations, and context will be the name of the cluster or the context or whatever it is. And current context will tell you which cluster you are trying to talk to right now. Kubectl also has a dry run, which is a fantastic flag to actually uh, dry run a resource, meaning your resources will not actually be created on the cluster, but it'll return you the output as if they have. So if you have a problem with your resource, it'll tell you beforehand. So depending on how much time we have, we can actually go through the demo. It's 7:15, so we can actually quickly run through the demo of this these things before we get into the Kubernetes objects. And I have on my own machine Kubernetes cluster running. You're still able to see my screen?
Yeah, we can see it.
Okay. So yes, so kubectl is the tool that we have, and it has bunch of operations that you can do. So I'm going to show you some of those. The one that we talked about is the kube config. Let me actually show you the kube config. It's stored at kube/config location by default. You can have it at a different location, but that's the default location at which it's stored. Just to make sure that you're all able to see. So this is the location, and this is the file. Uh, this is a cluster, so running on my local machine. So the server address is a local host. It's a service running at my local machine. I'm using kind for that, and this is one cluster information. The whole thing. Context is how it separates. So context name is kind demo. So if we do kubectl, if we ask kubectl to show us the current context, it will show this kind demo thing through this current context. And if we have multiple of these clusters, the current context will go to whichever cluster that we are trying to use. So in my case, there's only one context, but if we want to check that, if we do kubectl kubectl current context, it will show this kind demo, right? This is the this is what I wanted to show in kubeconfig. And with kubectl, you can basically connect. So for one of the things that we want to see, let's say if how many nodes are there in kubectl. So it's a very intuitive thing. So you would say kubectl, you want to get something, it's get, and you do nodes. So it will tell you that currently there is one node running. It's running from, well, many days. So we have only talked about nodes so far in Kubernetes architecture, so I'll not go and talk about other resources that we have not talked about so far. But this is the basic example of kubectl and how to use it, and where the kube config is, and how it sort of works. Any questions?
All good.
All right. Let's move on to Kubernetes basic objects. So Kubernetes namespace, and this is different from Linux namespace, right? It's a Kubernetes logical construct to separate out workloads that we deploy in Kubernetes cluster. So this is different than Linux namespace. It's a Kubernetes own construct. Uh, to each their own, it basically separates all your workloads into a namespace. And when you create a cluster, namespace called default already exists on the cluster. So the default namespace is created by default. You can create any number of namespace. It's a very cheap resource. It's just logical entry in its CD. This you can have tens, hundreds of those. There's no problem. Uh, Pod is a wrapper on top of a container. Uh, by that I mean a pod will have one or more container, but it is the smallest logical entity in Kubernetes. We will use all other objects that deploy a workload, basically create pods, right? So if you have deployments, if you have replica sites, if you have other objects, the other objects that actually create something of a workload, they create pod. So they manage pod in some or the other way, right? Uh, so they are more than containers. They are group. There, one or more container forms a pod. Standard Kubernetes mechanism would have one pod, but there are many use cases in which you have more than one pod, no, more than one container in a pod. For example, logging is a perfect use case. Whatever logs are generated by your pod, they could be redirected to something else, and that can be injected as a separate sidecar container in your pod. So sidecar is a additional container that does not do your services work, that is part of your pod specification. So uh, yeah, that's about pods. Deployment is a Kubernetes standard for deploying stateless applications. So majority of Kubernetes applications are deployed as deployments. So when we create a deployment, it creates a replica set, which then eventually creates pods, and we can basically tell deployment how many pods we want. We can, along with that, we have a bunch of other information that we tell deployment. A deployment is a controller. What that means is that if one of the pod dies, and we will be using the word pod from here on, no more containers. Pod is one or more containers. So we'll be using pod as a standard because that's the lowest unit of Kubernetes deployment, smallest unit of Kubernetes deployment. So uh, when we have deployments, they'll create one or more pods. Uh, Along with that, if one of those pod dies, for example, if you have a deployment that has a replica of 7, what that tells Kubernetes is that 7 instances of pods must exist in this deployment. And Kubernetes will work very hard to ensure that they do, barring few situations wherein it's not able to allocate those because there aren't enough resources. Barring those situations, Kubernetes ensures that whatever you asked for is provided to you. A replica set is exactly what exists between deployment and underlying pod. Replica set is the core controller that ensures that when a pod dies, a new one is created. When a pod crashes, a new one is created. When a pod is errored, it's restarted. uh, Everything is managed by replica set, and replica set is a controller that is used not just by deployment but many other many other um, Kubernetes controllers. So deployment is a type of a controller. Kubernetes config map is just a config map. It is just a map. It's just a dictionary that stores key value pairs. There is some metadata in it, but it is basically just a map, right? Secret is also a map, but it is, well, slightly more secret. It's only secret as long as you're not in cluster. If you have access to the cluster, then it's basically just a map. There's nothing secret to it. Uh, Secrets and config maps can be mounted as files in the Kubernetes pods, so that, let's say, if you are running a service, let's say you have a food delivery application, and one of the microservice is to accept order, right? Or to send to send order to the restaurant, right? So you have some configuration required for that service. That configuration can be stored in a config map, and that can be mounted as a file inside your pod, inside your container, which then your service can use information from that configuration to run. So in this case, it could be uh, in this case the configuration could be, let's say, what is the the number of uh, restaurants that you want to show, if you're showing number of hotels, right? And that could be a configuration. It could be a dynamic configuration, it could be a static configuration, it could exist in a config map, and that can be mounted inside your pod. So these are the basic objects. And again, I'll quickly move between demo and presentation. We'll not go through all of them. We might not have time to go through all of them, but I will share the resources. Kubernetes namespaces can be created as Kubernetes create namespace and namespace name. Again, Kubernetes namespace is a very, very cheap resource. There's no limit. There's virtually no limit to how many you can have. Uh, so yeah, so always a good idea to separate your workloads. Uh, right. So that this could be as simple as, let me clear these things. It could be kubectl create namespace. Let's say uh, workshop namespace, right? Just to ensure that this does not exist before we can check NS's namespace. But yeah, there is no namespace named workshop namespace here so far. Nothing has changed since past 132 days. So we can create this workshop namespace, and it will go and create that. It's created 2 seconds ago, right? We can also check when we can also have this done by a YAML file. We can do give me a YAML file. I don't really want you to create resources, just do the dry run. So it will create a YAML file. Uh, yeah, it's fine. We need to call it dry run equal to client now. I have a newer version of kubectl, so it's fine. So we'll say uh, dry run equal to client, and it will do this file. It's a It's a file that can be stored in your Git repo if you want your namespaces to be created in some sort of pipeline. And this can be done for nearly all resources, for which, the dry run basically works for all resources. And so does -u YAML. Right. So pods basically, there are one or more containers. They are basic building blocks of all applications. And pods require image name and a tag. We talked about Docker image at the beginning. The Docker image has image name and it has tag, which follows similar version. Um, it uh, we also have a bunch of other configurations such as volumes, volume mounts, environment variables, uh, and like where to pull those environment variables from, whether to use config maps or secrets to get those environment variables from, and that kind of thing. Pod by themselves don't have controllers. They're managed by other controllers. If you create a pod yourself, which is not a good idea, unless that's something that you want to test or quickly test something, but you would not create pods yourself to deploy anything virtually. So because they're left unmanaged, you have to manage them yourself if you deploy them yourself. If you create those using a controller, then those controllers manage those pods for you. So very important to make sure that uh, pods are created through a controller. And the kubectl explain is something really cool that I'm going to show you. So even if you have worked on Kubernetes before, I have some idea of what Kubernetes is. uh, you'll be really able to explore a lot of resources to great level with kubectl explain. It's one of the best uses of kubectl. We'll look at that. uh, in fact, we'll look at that now. So you have kubectl. We created a pod. We have not created a pod. We have a namespace created here, right? Uh, so let's see if we have any pods. Yeah, so I have a pod called 2 containers. Interesting, that I created some time ago. So if I do kubectl get pods and provide a name, then it'll give me a specific pod. If I do -o YAML, then it will give me the YAML of this pod. It's created. So it has. Okay, let's do less actually, so we can see this. So it has an API version which is v1. Kind is pod. Kind is the type of the Kubernetes object that you're trying to create. It's a kind of the object that you're trying to create. So the kind is pod. In the previous example, in the namespace, the kind was namespace, right? The metadata, you can ignore these managed fields. Don't really need to know about that like it's managed by Kubernetes. We don't really care about that. The name is 2 containers, the namespace, which is default currently. We can create it in our namespace as well. It uses some image from QA, simple service. Okay. And it has 2 containers, right? So it has 1 container, it says 2 containers. So one is this container, which has bunch of configuration, and there is no other container. So I think it's probably wrongly named. It's probably wrongly named. So this is the image that it requires. It also has name called CC. It has image pull policy of if not present. I think this example is from Kubernetes by example. I have linked to Kubernetes by example in the resources tab, resources uh, list at the beginning of the presentation. So you can have that. The image pull policy is really interesting. Image pull policy tells you when to pull the image. Standard image pull policy is if not present, meaning Kubernetes will actually pull your container image only if the image is not present. On the development, let's say you don't want to create new tags and you just want to use the same tag to push images, then you would need this image pull policy as always. Otherwise, Kubernetes will use the previous image that it pulled at some point, and you'll not be able to test your latest changes, right? And the example, like the kubectl explain that I wanted to show you, is that this is a very long spec, right? So it has this API version, kind, metadata, and metadata is again huge. It has spec and it's all of these things, so you don't really know where to start from, where to see what is happening or what specific field that you might need to set, or where a particular field is in spec, right? And that's where kubectl explain plays a really important role. And this works for all resources. It also works for your own resources that you can add to Kubernetes. So if you do kubectl explain pod, and it will give you what pod is. So pod is, to create pod, you always need kind as pod, version as v1. It also has description. The description is the description of the resource, and the fields that it has. So this is not the property. The fields that it has are the properties that exists in the YAML. It's going to have API version, which needs to be v1. Kind needs to be pod. It's also going to tell you the type of the object. So string and bool are some of the final stages. What that means is there's nothing else after that. Uh, Metadata is an object, which means that it is going to have more properties. Uh, it has spec, which is also an object, which means it is going to have more properties or fields. Status is also going to have more properties or fields. So we can go through any of that. We can do pod.metadata, for example, and it will tell you what pod.metadata is formed of. So, and it's quite a bit of things. So again, let's do less. So it's v1 pod metadata resource. Its resource metadata is formed of annotations, which is a way to mark an object with something. It's a key value pair. Uh, cluster name, again, most of those things are going to be generated. Creation timestamp is going to be a generated value. So whenever we create a resource, it's going to have a creation timestamp. And as you can see, uh, these are final things. It's a map of string. So you can't do metadata dot spec dot something because there's nothing after metadata. There's nothing after cluster name. There's nothing after creation timestamp, right? Uh, so these are final objects. Finalizers is how Kubernetes determines whether an object will be deleted. So you can read through this documentation and it'll give you a very good idea about each of those properties. You can do this for anything. So you can do this for, let's say, spec, which is the core part that we need to set most of the times. This is activation deadline second, affinity, all of those things. This is our most important thing, right? Containers. So as I said before, pod is a set of containers, a list of containers, right? So you can have one or more containers. Um, it technically is list because you can only have one uh, container name. You cannot have duplicate containers name, but it's a list of containers belonging to a pod. Once you create a pod with, let's say, 4 containers, it's always going to be with 4 containers. You will not be able to add an extra container to that, is what it says. And you have bunch of other configurations and you can navigate through that. So this container is a list of objects. So there is a further thing that you can go further in that. And this is where kubectl explains, for example, we can do dot containers and it will give you a list of things like, so each containers is a list of object. So it's a list of arguments and each argument is form of these things. So command is the entry point, arguments are argument, environment variable is what environment variable you want to set, image full policy, that this is the one that we talked about. If you're using latest tag, for example, uh, defaults to always if you're using latest tag in your image. Otherwise, if not present, you have to set those things yourself. uh, you have to set those things yourself. These are the 3 possible values. So you can actually go through each of those properties that you want to do with kubectl explain. Instead of going through the documentation, you can just look at what specific thing you need to do, and kubectl explain will actually tell you. So this is one of the best resources in trying to understand any Kubernetes object, and this works for everything. So it's not just pod. It also works for, let's say, if we do namespace, it's going to work for that. It's going to tell you what it is. Uh, we don't need less probably here. Yeah, it's going to do that. You can also do that for deployment, and it's going to tell you everything about the deployment, where each fields are, what it is. And this is a really, really powerful resource. Uh, all right. So deployments are Kubernetes standards for stateless applications. Kubernetes deployments create replica sets, which in turn creates pods. They have their own controller. Their lifecycle is managed. Pods lifecycle is managed by deployment controller. If you create a deployment is going to have a number of pods, and those pods are going to be created by a replica set, which is effectively managed by deployment. So deployments controller manages this replica set controller, lifecycle of replica set, and replica sets controller manages lifecycle of pods. Is this clear? This is kind of fundamental in how applications are deployed on Kubernetes. No questions? All right. So replica sets are used by controllers such as deployments, where it manages the desired and actual number of instances, right? So as we talked about earlier, your desired state and actual state is always maintained by Kubernetes. Kubernetes does this. Kubernetes scheduler and Kubernetes controllers do their best to manage the desired and actual state of all the instances of your pods, right? These are in turn, these need to be managed by someone. So replica set controller is a mechanism to that basically is used to manage that. These are created automatically when you create a deployment. You don't need to go and create a replica set. It's created automatically when you create a top level controller such as deployment. It's used for rollbacks and rollouts. So if you want to roll out a new service, the way Kubernetes does it, it's really, really interesting. It's like if you have 3 instances of your V1 service and you're rolling out V2, right? You want to make sure that it's rolled out in a blue-green manner, so that when you have your load, all of your load coming to V1 service, and when you roll out to, let's say, V2, you have 3 of those controllers. One of those controllers goes to V2, and 1/3 of your load is redirected to that V2. Rest is on V1 of your service. Uh, then the second pod gets created with V2, and 66% of your load goes to V2. And then finally, when everything is stable, the third pod of your V1 goes down, and 100% of your load shifts to V2, right? And that is where replica sets play key role, because the way deployment does it is it creates a replica set of V2 with 0 pods, and replica set of V1 has 3 pods. Uh, then when we roll out, it creates one replica in V2 replica set, and reduce the replica count from V1 replica set by 1. So the total count is still 3, but one of those is going to be V2. Once everything is working, it'll do the same thing. It'll increase the number of replica count on V2 replica set, and reduce 1 from V1 until V1 reaches 0. It never deletes replica sets. It just says the replica set says 0, so that we have history and of all the rollbacks, and we can roll back to a particular replica set. All the configuration of a replica set is virtually immutable, so we can always go back to its state, and every time we change something in deployment, a new replica set is created to ensure that rollouts and rollbacks work properly.
This is pretty interesting. Is this to catch any bugs from V2 early?
It's not just for that. It's one of the mechanisms. You can basically change your container image in your deployment and have all your services move to V2 in an instance. But standard blue-green deployment will require you to shift workloads. This is possible in Kubernetes, and the mechanism it uses is replica set. So there is also get, getting bugs is one of the side effects of it, but that's not really the purpose. The purpose of it is to ensure that your workloads are balanced. For example, if you have a very large, so for example, if you imagine you have application like Facebook, for example, and you have a feature like timeline, right? You can't really shift everything to V2 right away because V1 is still serving large number of load. So
Yeah.
you do require V1 to be up until V2 starts taking up load and all new requests redirect to V2.
Okay.
So that is primarily the mechanism of it. But if if you are in the middle of a rollout, that's not really the point where you would uh, a specific type of deployment to catch bugs. I mean, that does happen, but it's an ancillary benefit rather than primary motivation.
Okay. Okay. And how long it depend? How long everyone would be getting V2 depends on how many people are using your application and how long it takes to move them from V1 to V2, right?
No, it's like you can actually enforce that. You can force people to drop their connections after a certain point of time. That really depends on your service and implementation and its configuration. So Kubernetes rollouts allow you configurations by which you can do this in a fairly reliable manner.
Okay.
But how to deal with connections? It's so. For example, the way to think about it is like this: if you're playing a multiplayer game, let's say, if you're playing uh, let's take an example everybody knows, Age of Empires, right? And for whatever reason, uh, new version of that service, like service to do something in that game is being deployed. Let's say it could be matchmaking, it could be something else, right? Do you really want people who are in the game to shift to new services of matchmaking? Probably not, because they have already been matched to other players and they are in the game, right? You do want new players to go to that, right? So it's fine if old players remain attached to a server that's serving old services, uh, because they are eventually going to get off that server, but new requests would come to the new service, and that kind of thing. So these are configurations are possible, and these would be like when you have highly scalable service, highly scaled service, you need to take these things into account. But there might be some instances in which you say, for example, there is you're playing in the same gaming example. Let's take you're playing Fortnite, for instance, and there is some well-known uh, mechanism to cheat for players, right? And you have a fix for that mechanism to bypass that mechanism. And some people who are playing right now in a game are leveraging that mechanism to cheat, right? But your new service detects that, right? Or your old service detects that but can't do anything about it. So do you want those games, do you want those player connections to be dropped and force them to move to new servers? Probably yes.
Okay.
So it depends on the use case, what you want and how it's implemented. So it's really a way of looking at what your functionality is and how it fits into the service architecture. Kubernetes provides mechanism to do both.
That's pretty interesting. Okay, thank you.
All right. I see a few things in the chat. Yes, those are service versions. Those could be your like those would be your those could be your pod versions, container versions. Those could be your versions internally of the services. But they would need to be tracked at a container version. Yes, you're right. All right. Uh, Moving on, config maps. We talked about config map. Config maps is just map. I'm not going to go through the example of config map. It literally is just map. I'll see if there is an existing config map on my cluster. This probably is. I can show you what it is. Uh, yeah, there is. Yep. So just want to do that. Let's do this. And if we do hyphen YAML, it'll like this. Yeah. And again, forget about this metadata. It's annoyingly painful, but yeah, this is the map. So the tech, this is the key config map data text. It's formed from that. It's the key. These are the key value pairs, right? So it literally is just a dictionary that exists in Kubernetes. So all right, and secrets are pretty much the same. I don't think I have even covered secret example. It's pretty much the same. There are few types of secrets depending on what you're trying to do. Like standard is a generic opaque secret. Basically means things will be base64 encoded. Yeah, it's opaque. There's also Docker config JSON and a few other types of secrets uh, used for very specific use cases. So we're not going to cover that. Those are very niche and very specific use cases. Docker config JSON is pretty much required for all if you're going to use a private repository for Docker containers. But apart from that, it's not required. Okay, services. So services provide a service discovery mechanism. So if we look at our pod on the cluster, uh, so yes, you can see pod IP. There is a thing called pod IP. Let me actually grab that so that it's better visible. Yeah, so this is the pod IP. Currently it's 10.244.0.9. So whenever a request is sent to this particular pod, the two containers pod, the request is going to redirect to this thing, this IP, and it's going to happen because uh, there's nothing else, right? If I write a service on top of it that looks after this pod, it's going to redirect it to this particular pod. But if in case it goes down and a new pod comes up, it's going to redirect it to the new pod. If I don't have a service, I can't really uh, I can't really uh, keep things going when pods die. Pod dies, for example, right? So that's why services provide a crucial function of service discovery. So there are four main types of services. Cluster IP service is a service that runs really well inside a cluster. It has an IP associated from inside the cluster. So if we create a cluster IP service, it's going to get an IP from inside the cluster, which means that it will be reachable only from inside the cluster. So if you need a service that is consumed internally, for example, if you have a token service, which is part of, you have a token service which is separate from auth service which validates token, but it's only consumed internally. You know, users on the internet cannot call this service, or users outside your cluster cannot call this service. It's only your services talking to this service. Then cluster IP makes perfect sense. Node port is a service which basically maps a port on your machine, on the machine on which the pod is created, to the pod, to the pod's port. So this is very useful when you want to test something locally, but you would not use this in our productions. Uh, you have load balancer service, which basically goes and creates a load balancer on your provider. The provider could be anything, as long as you have a Kubernetes support for that provider. It will go and create. So, for example, there's support for AWS, GKE, Azure, any number of cloud providers. So it will go and create a load balancer there, and the load balancer will redirect traffic to your service if you don't have anything else in between. But generally you would have something like an ingress. We'll talk about that in a few slides. And then you have headless service. Headless service is basically cluster IP service without IP. So it basically it's used for when you need a name of a service to do something. So yeah, we have talked about kubectl run. Uh, I don't think we have enough time to go through all of that, but I'll quickly explain what these are. Kubectl exec allows you to go inside the container of like one of the containers in your pod and run something. So if you have an error, if you want to go and check something, whether everything is set up properly, whether configurations are in the right place, whether your service is doing the right things, if the service is up inside your pod, if your pod is up but the service is not responding, you want to go and see what is happening, you can do kubectl exec to go and see. There is kubectl logs, although this is something that I never use, because there are much better alternatives to kubectl logs. Kubectl log allow you to get the logs, everything that is written to standard output and standard error streams, to be propagated uh, on your screen. So you can do kubectl logs to see what's happening inside your container. It's hardly ever used from me. I personally prefer Stern, and we'll talk about that. Uh, and all right. In advanced concept, so we already talked about Kubernetes basic objects. Some of the advanced concepts are Kubernetes service accounts. Service accounts. So service accounts is how Kubernetes knows who is trying to do what, right? So there are real users like you and I who will try to get list of pods and whatnot, but your service is also an agent who exists inside Kubernetes ecosystem, and that service can also do some operations on your cluster, right? So that is a basically robot account. So that is Kubernetes uses service accounts to manage those things. uh, all of those are used to like all like when you create a Kubernetes clusters. In fact, service account is quite important, so let's actually go and see what exists on our cluster. So we currently only have default as a service account. If we because we are in the default namespace, it's a namespaced resource. If we look at those from all namespaces, we will have all of those. And as you can see, there is a workshop namespace. So every time you create a namespace, you create a service account. And again, service account is a fairly cheap resource. Uh, all of those service accounts, so for example, namespace controller wants to do something, then it uses namespace controller service account, which has certain permissions to do some things. If node controller wants to do something, which is a very limited set of things, then it will do something. The deployment controller is the same thing. Deployment controller has its own service account, and it will be able to do those things, do only those things which for which it has permissions in that account. So it's a access control mechanism. It's the core access control mechanism that Kubernetes uses. We have daemon sets. We talked about Kubernetes deployments, wherein deployments can create number of pods on Kubernetes cluster. Uh, and any number of pods can be created in Kubernetes will try to distribute Kubernetes scheduler will try to distribute its workloads uh, fairly evenly. But if you have a very powerful machine and two other machines that are not that powerful, in which case you might see one machine having a lot of workload. In case of daemon set, one node gets one pod of that daemon of a daemon set. This is really useful when you want to, let's say, get crash dumps or logs or traces. You know, you only need one agent working on a particular node. So daemon set is the perfect use case for that. Uh, Statefuls is because, of course, why wouldn't you want a storage, right? Deployments, so far, deployments and daemon sets, we have not talked about storage. Stateful sets would allow you to have uh, storage attached to your containers through persistence persistent volumes, persistence mechanism. It's called persistent volumes and persistent volume claims. Uh, we talked about Kubernetes services and how they make it easier, how they make it possible for us to connect to pods. Ingress basically sits between your load balancer and your set of services so that you don't need one load balancer per service, right? You can have a single load balancer and your ingress will do the redirection. Your load balancer will talk to your ingress, and then your ingress will basically send your distribute traffic to, well, not ingress controller will distribute requests to your services. Nginx is the most popular one, but you also have HA proxy and other things. Uh, Kubernetes also has jobs and cron jobs. Those who have worked on Linux probably already know what cron jobs are, and they are jobs that are run to completion. They do something and then execute, and the execution is completed. Uh, you have cron jobs which run at a specific time. Right. Any questions on this? Yes, we talked about Kubernetes service accounts. We talked about daemon sets. When we create a new node, a new pod will be attached because there's only one daemon set per pod. Um, we talked about use cases. We have a log collection. We have node monitoring, traces on every node. We only need really one agent there. So daemon set is a perfect use case for that. Stateful sets have identical pod spec, container spec. They maintain a sticky identity for their pods. What that means is that they basically attach themselves to the persistent persisting resources. As we have looked before, that Kubernetes are short-lived resources, but uh, these can be attached to a long-running resources such as database, for instance. Uh, Ingress, we talked exactly about that. We have ingress controller that uses ingress to redirect to service. There is one routing rule that goes to one service, but we can have multiple such services, and the same single ingress with multiple different routing rules would suffice. That way we will only need one load balancer, and load balancers are quite expensive. We talked about ingress controllers. Nginx is the most common one. There's HA proxy and traffic, which are also fairly used. Kong is the default one on Google Cloud, I believe. We also have Istio service mesh, sorry, uh, which uh, which works a little differently, but it serves the same use case. Uh, so ingress is a ingress rule, ingress resource. However, ingress controller is a controller that enforces that rule. Um Jobs run to completion. They do specific number of operations and then complete. They don't keep running. They stop running once they're done. Cron jobs are jobs with a schedule. So yeah, they clean up. You basically can use them in variety of contexts. So for example, if you want to run your test pipeline at a specific time, it could be a cron job in Kubernetes. Uh, yes, we talked about scheduling, and we discussed how we should not use a specific we should not target a specific node. In the previous GPU example, if you remember, we talked, if your workload requires GPU and you only have five nodes with GPU, then you'd probably need a node affinity, and we'll go through all of these taints and tolerations. So taint, when you taint a node, it's literally tainting a node. uh, what that means is that you say that don't install things on this node anymore, right? And this, if you still want to install things on that node, if you still want to run your pods on that node or your workloads on that node, create deployments on that node, you need to be able to tolerate that tent. If you tolerate a particular tent, then you can run workloads on that. And this can be used specifically, for example, in the GPU example that we are talking about, we can have a tent saying that uh, GPU exists equal to true. And if if your workload requires GPU, then you need a toleration that says, yeah, schedule if only GPU exists, and then your workloads with GPU will only go there, right? Node selector is the oldest scheduling mechanism. It points to a specific node. So if you, again, this is not the best use, because you don't get all the advantages of Kubernetes scheduler, which is quite uh, it's quite well developed. So node selector is not the best idea to deploy workloads, but there might be certain instances in which you say, I want my workload to run only on this node. That's where you would use node selector. Pod affinity and anti-affinity is about whether you want your pod to run where other pods are running. So let's say you want your pod to run, if you're trying to run a caching pod, you want to run it where your web service runs. You say, I have a pod affinity toward, like, this pod has affinity toward web service pod, and Kubernetes will try, it will not guarantee, but it will try to, and there are several mechanisms to see if you really want it. uh, it will try to ensure that this caching pod is scheduled along with uh, the web service pod. And anti-affinity is exactly opposite of that. It will try to ensure that your pods and the pod that you don't like are not scheduled on the together on the same node. Node affinity and anti-affinity is about nodes in the context. Uh, if you like particular set of nodes in our GPU case, for example, if you like the nodes that have GPU, uh, so you can say, well, I really like my workload to go on that node, although it's not a strong preference. In which case Kubernetes will try to do that if it's possible. If it's not, then it won't. Again, there is a stricter way to do that at a time of scheduling, and anti-affinity is exactly opposite to that. For example, if you want to run your web server, you say, I really don't want to run on GPU because I don't need GPU. So try to schedule me on nodes that don't have GPU. But if you can't, then that's fine. So that's how node anti-affinity work. Taints and tolerations, we talked about that. We actually briefly talked about all of those four. Uh, so we need to have this, like, if there is a meaning of life is 42, then we need to have that toleration for things to schedule on there, right? And this is how we would write a toleration in our spec, in our it's part of the pod spec. Node selector, it's basically a key value pair. If node has, if you use node selector, then it'll only it'll only schedule your pods on the specific nodes. Again, this is not the best use of Kubernetes scheduler. We have affinities. Node affinities and node anti-affinities are generally preferred, like they're at a higher, uh, they're given higher weightage than pod and affinity and anti-affinity. And the last thing that I want to talk about is custom resources. As I said before, Kubernetes allows you to have custom resources, wherein you can design your own resources, and Kubernetes will treat them as if they are Kubernetes native resources. You can also write controller for your own resources. You saw the deployment controller had the service account. Uh, so there's a deployment controller, but if you write your own object, let's say an object called cell phone, right? And then you can have an operator for cell phone. Uh, and then that would take care of the life cycle of Kubernetes object, Kubernetes custom resource of type cell phones. Um, you can use your own controllers to manage these resources. There is a declarative API for that. The most famous project for doing that is Operator SDK. It's one of the most extensively used projects in Kubernetes ecosystem for Kubernetes extensibility. Uh, and yes, I think that is pretty much it. These are other interesting projects that you probably want to keep an eye on. There is Customize, which does really amazing things with your Kubernetes resources and custom resources. NY Proxy is a service mesh proxy. Istio is a service mesh. Uh, Helm is a standard mechanism of deployment of uh, Kubernetes resources via charts. So we have Helm charts to deploy resources on Kubernetes. And there are Helm Operator. Helm Operator is an operator written by this Operator SDK project. It basically manages the life cycle of Helm charts. It can manage the life cycle of Helm chart by creating Helm resource object, Helm release objects. So these are some of the interesting projects that you may want to explore in future. So I think that covers the scope of it. If you have any questions, I'll take a few minutes to answer those.
I actually have one. Do any of the resources you shared at the beginning kind of go over how to deploy a microservice, like step by step? Because it's a bit hard.
They do.
Really?
They do. They do.
I've tried to play around with Kubernetes, but with small websites and things like that, it's not the same.
Yes, they do. So in the early part of the work, just a second. Let me go to the beginning of the presentation. Where is it? Yes, so Kubernetes by example actually tells you quite a bit. There is interactive tutorials on Kubernetes that allow you to deploy the whole service, and you can actually try examples from interactive tutorial and Kubernetes by example on Kubernetes Labs. But both of these places have at least one complete example of deploying a microservice.
Okay.
Yeah, but these are usually smaller services. Kubernetes by example is probably the most comprehensive one. There's no limit to how complicated your service can be. And if you're writing those in languages like Go or Node.js, the size tends to be really, really small. But there are some examples that walk you through both of these places actually walk you through those.
Okay. Question: Do you have to have DevOps in your job title to be able to play around with these things, or do people, even like full stack engineers, get to kind of touch Kubernetes and things like that?
So a lot of things are changing from the point of view of DevOps. So for example, I'm primarily an application developer. I'm not a DevOps developer or DevOps engineer. Um, so through application developers do need to know if they have their deployments on Kubernetes, they do need to know some Kubernetes, some basics of Kubernetes to be able to investigate the problems that they face. And you also probably need to write quite a bit of pipelines. Another thing that's happening with Kubernetes because of Kubernetes is that the development and DevOps roles are sort of merging. There are a lot of SRE roles that take care of your infrastructure for you, but you have to write your own pipelines as a developer. Uh, that basically means you need to know how things work on Kubernetes. And if you are developing, if you are developing in a cloud native fashion, you probably need to extend existing Kubernetes structure to accommodate your own custom resources, in which case you would require advanced level of Kubernetes as a developer. Uh, with DevOps, you would need a quite comprehensive understanding of things. Uh, but as a developer, you require basic knowledge of how to debug things and how things work and how to debug things and how to work with custom resources and how to work with services and service accounts and that kind of thing. But as a DevOps, you would need to know a lot more.
Yeah, makes sense. Okay, thank you.